Welcome back to AI.Code.Cast. Today, we're going to be taking a deep dive into this problem of finding duplicate subtrees within a binary tree.
Ah, yes.
And, it might sound a little abstract, but, I promise it has some really interesting applications like in, things like plagiarism detection and data compression.
Oh, absolutely. It's really cool how this seemingly, theoretical problem pops up in all sorts of practical areas.
Right. So before we jump into like solutions and all that good stuff,
Yeah.
maybe let's start by just, really clearly defining the problem.
Yeah, definitely.
So we're given a binary tree, and
Well,
our mission is to find all the subtrees that are like exact copies of each other.
exactly. And it's
Yeah.
important to emphasize that we're not just looking for, individual nodes with the same value like scattered throughout the tree.
Right?
We're talking about like entire branches that are identical in both their structure and the values in each corresponding node.
Yeah, it's like, if you're comparing two family trees, you're not just looking for people with the same name. You're looking for like entire branches of the family that are like mirror images of each other.
Exactly. So for instance, if we had one tree representing the sentence, see Spot runs fast, and another representing Spot runs fast, Jane sees Spot, we'd want our algorithm to flag Spot runs fast as a duplicate subtree because it appears identically in both trees.
Okay, so now we've got the problem crystal clear.
Yeah.
Where do we even begin? Like, what's the most like naive, straightforward way to tackle this?
Well, I think the most intuitive approach that probably comes to mind first is just brute force comparison,
Okay.
which basically means we compare every single subtree in the tree to every other subtree.
Okay.
Yeah.
I can already see where this is going.
Yeah.
That sounds like it could get really computationally expensive, especially if we have like a massive tree with tons of nodes.
Yeah, you're absolutely right. The number of comparisons we'd have to make would just explode.
Right.
Making this approach really inefficient for anything beyond like the tiniest of trees. I mean, technically speaking, the time complexity would be O of n squared, where n is the number of nodes.
Right, which is not something we want.
Yeah, not ideal.
So brute force is out the window. What's a smarter way to do this? Like, what if we try to represent each subtree as some kind of unique identifier or like a fingerprint?
Ah, now you're thinking that's a really clever idea.
And then instead of comparing the entire subtrees, we could just compare these like fingerprints.
Exactly. And one way to create these fingerprints is to use a string representation of each subtree.
Okay, I like where this is going.
So we could traverse the tree in a specific order, like pre-order traversal, and as we visit each node, we add its value to our string.
Okay, pre-order traversal, just for those who need a refresher, means you visit the root node first,
Yeah.
then the left subtree, and finally the right subtree.
Right. And to distinguish between empty subtrees and subtrees with a single node, we could use a special marker like hashtag tag to represent a null node or an empty subtree.
Well, it's smart. So for example, if we had a subtree with a root node of 1, a left child of 2, and no right child, the string representation would be 12.1, hashtag, hashtag, hashtag.
Exactly. And the cool thing is that two identical subtrees will always have the same string representation.
It's like giving each subtree its own unique ID card.
Precisely.
But wait a minute, wouldn't we still need to compare all these string representations to find the duplicates? So we've just shifted the problem from comparing trees to comparing strings.
That's true, but that's where another powerful tool comes in, the hash map.
Okay.
You can think of a hash map like a super fast dictionary where we can quickly look up a word and see its definition.
Okay, I'm following.
In our case, the words would be these string representations of our subtrees, and the definitions would be whether or not we've already encountered that subtree before.
So as we generate the string for each subtree, we check if it's already in our hash map.
Yeah.
And if it is, bam, we know we found a duplicate. If not, we add it to the hash map and move on.
Exactly. And this approach, using the string representation with the hash map, allows us to find those duplicates much, much faster than brute force, because we only need to traverse the tree once to generate all those string representations.
That's really clever. But I do have one concern. Won't these strings get really long for large trees?
Yeah.
Especially with all those hashtag markers for empty subtrees. It seems like we could run into some memory issues.
That's a sharp observation. You're absolutely right. String representations can become quite lengthy, and memory usage could become a concern, especially when dealing with massive trees.
Right.
So it seems like we need a more compact way to represent these subtrees, perhaps without relying on strings at all.
Yeah, like what if instead of strings we use numbers? Like each subtree gets a unique numerical ID.
That's an interesting idea.
But the question is, how do we assign these IDs in a way that guarantees identical subtrees will get the same ID?
What if we use a triplet system? So each subtree's ID is based on three things: The ID of its left subtree, the value of its root node, and the ID of its right subtree.
Okay, I'm intrigued. So let's say we have a super simple tree where the root node has a value of 1.
Okay.
We could just arbitrarily give it an ID of, say, 100.
All right.
And if it has no children, its left and right subtree IDs will
Uh,
be. Well, what do we use for empty subtrees in this system?
We could use a special reserved ID like 0 to represent an empty subtree. So our root node with no children would have the triplet 0, 1, 0.
Got it. So now let's add a left child to the root with a value of 2. Since it also has no children, its triplet would be 0, 2, 0. Right.
Exactly. Now, to give our root node its new ID based on its children, we need to combine these triplets in a way that makes sense.
Right, because we can't just concatenate them. Otherwise, we'd end up with these like super long numbers that defeat the purpose of using numerical IDs in the first place.
Yeah, we need something more elegant.
What if we treat this triplet as like a unique combination and use it as input to a hash function?
Ah, brilliant. That would give us a single unique hash value to represent each subtree.
And that hash value becomes the subtree's ID. And just like with the string representation, 2 identical subtrees would always produce the same hash value.
Exactly. And because we're dealing with integers, this approach should be much more memory efficient, especially for large trees.
This is all starting to make sense now.
Oh.
But before we get too carried away, how do we actually use these hash values to find the duplicates?
Well, we can use that same trusty tool we talked about before, the hash map. We can store these hash values as keys in the map.
Right.
And if we encounter the same hash value more than once while we're traversing the tree, we know we've found a duplicate subtree.
It's like spotting the same fingerprint twice.
Precisely. And comparing these integer IDs for duplicates is super fast, much more efficient than comparing those potentially long strings we were dealing with earlier.
This integer ID approach is really slick. It feels like we've managed to break down this complex problem of comparing these tree structures into a much simpler problem of comparing numbers. But wouldn't actually coding this up be a bit tricky? I'm imagining lots of recursion to traverse the tree and generate all these hash values.
Yeah, you're right. It does involve recursion, but I promise it's not as complicated as it might sound at first.
Okay, good.
We can break it down into smaller, manageable steps.
Okay.
So maybe I can sketch out like a basic pseudocode outline to illustrate how we could approach this.
Wait, before you do that, let's actually pause here for part 1. We've covered a lot of ground from the basic problem to brute forcing it and then brainstorming these 2 clever approaches. String representation with hashing and integer IDs with hashing.
And we've highlighted some of those potential pitfalls and memory considerations along the way, which is crucial when designing efficient algorithms.
Exactly. So join us in part 2 where we'll roll up our sleeves and delve into that pseudocode and really get into the nuts and bolts of how to implement this integer ID approach.
Looking forward to it.
See you there. Welcome back to AI.Code.Cast. In part 1, we tackled that challenge of finding duplicate subtrees. We explored brute force, and then we came up with those 2 pretty clever approaches using hashing. And now I think it's time to roll up our sleeves and really dive into the pseudocode for that intriguing integer ID method.
Absolutely. So just to recap, our goal is to represent each subtree with a unique numerical ID based on, the ID of its left subtree, its root value, and the ID of its right subtree.
Right, like a fingerprint, but with numbers instead of those swirls and loops.
Exactly.
So walk us through how we turn this idea into an actual algorithm. Like, how do we code this up?
Okay, so picture this. We have a function called, let's call it getSubtreed.
Okay.
This function takes a node as input, and it spits out the unique ID for the subtree that's rooted at that node.
So it's like asking the node, hey, what's your ID based on your family tree?
Exactly.
Okay, so what happens inside this getSubtreed function?
All right, so first things first, we check if the node is empty. If it is, we just return our special reserved ID, which we decided was 0.
Right.
That represents an empty subtree. This is our base case, our bottom rung of the recursive ladder, if you will.
Makes sense. We need a starting point for that recursion. Otherwise, we just keep going down forever.
Exactly. Now, if the node isn't empty, things get a bit more interesting.
Okay.
We need to calculate the IDs for its left and right subtrees, and we do this recursively.
So we call getSubtreed again, but this time with the left child as input, and then again with the right child.
Exactly. And now we have those 3 crucial pieces of information.
Yeah.
The left subtree ID, the root value, and the right subtree ID.
Right. It's like we've gathered all the ingredients for our unique ID.
Exactly. We've got our triplet, left ID, root value, right ID.
And that triplet captures the essence of that subtree.
Right.
But now we need to turn it into a single unique ID. Remember we talked about using a hash function for that?
Absolutely.
Right.
We feed this triplet into our trusty hash function, and the output of that function becomes the unique ID for this subtree.
Okay, so then we store this ID in our hash map along with like a count of how many times we've seen it.
Precisely. So if we stumble upon that same ID again as we're traversing the tree, we know we've found a duplicate.
It's like recognizing that same fingerprint twice.
Exactly. And
Yeah.
because we're working with these integer IDs, comparing them for duplicates is blazing fast, much more efficient than comparing those potentially long strings.
I'm really starting to see the elegance of this approach.
Yeah.
But before we move on, are there any potential pitfalls or things we should be wary of when we actually go to implement this?
That's a great question. One thing to always keep in mind is our choice of hash function.
Right.
We want a function that minimizes the chances of collisions where two different triplets accidentally produce the same hash value.
Right, because a collision would make us think we found a duplicate when we actually haven't.
Exactly.
What else should we watch out for?
Another thing to consider is, what happens when we're dealing with trees that have a huge number of nodes? Even though integer IDs are generally more space efficient than strings, if our hash function is spitting out these really large integers, we could still potentially run into memory issues.
So choosing the right hash function and being mindful of those potential memory constraints is super important for making this approach work smoothly.
Absolutely. It's always a balancing act.
Right.
But that's what makes algorithm design so interesting. Now I think it's time to shift gears a bit and talk about, how this whole duplicate subtree problem actually plays out in the real world.
Yeah, let's do it.
We touched on plagiarism detection earlier, but there are so many other cool applications.
Okay, tell me more.
One area where this technique really shines is data compression.
Yeah.
Imagine you have this massive data set with a ton of redundant information.
Okay.
By identifying those duplicate subtrees within the data structure that represents this data set, we can essentially replace those duplicates with references.
Okay. So instead of storing the same information multiple times, you just point back to the first occurrence.
Exactly, which can drastically reduce the storage space needed.
That's really clever.
And this principle applies to all sorts of data, from text documents to images, even to complex 3D models.
Wow.
Another fascinating application is in compiler optimization.
Compiler optimization. I'm not sure I follow. How do duplicate subtrees relate to making code run faster?
Well, you see, modern compilers are incredibly sophisticated.
Okay.
They analyze your code, and they're constantly trying to find ways to make it more efficient.
Quick.
One common optimization is identifying identical blocks of code that can be combined or reused.
Wait, so you're saying the compiler can actually look at the code as a tree structure and then use our subtree detection techniques to find these duplicate code blocks?
Precisely.
That's amazing.
By replacing those duplicates with just a single instance, the compiled program becomes smaller and faster.
It's like streamlining a factory process to get rid of all those unnecessary steps. This is really mind-blowing. We started with this seemingly abstract problem of finding duplicate subtrees, and now we're seeing how it connects to all these real-world applications like plagiarism detection, data compression, and even making our code run faster.
It really is amazing.
It highlights how these seemingly theoretical computer science concepts can have a huge impact on our everyday lives.
It's a testament to the power of algorithms and how understanding these fundamental building blocks can unlock so much potential. Now, we've explored these two fantastic approaches for finding exact duplicates.
Right.
But what if we want to venture into the realm of similarity? What if the subtrees aren't exactly identical, but they share some structural resemblance?
That's a great question. It seems like dealing with similarity would add like a whole new level of complexity to this problem.
It does.
But I have a feeling there are some clever ways to approach this as well.
You're absolutely right. And in part 3, we'll step into that intriguing world of tree similarity and explore some of those cutting-edge techniques that are really pushing the boundaries of what's possible.
Welcome back to AI.Code.Cast. We've come a long way, from those brute force comparisons to those really clever hashing techniques, all in pursuit of, tracking down those duplicate subtrees.
Right.
But like we hinted at the end of part 2, the real world,
Yeah.
it likes to throw us curveballs.
It does.
What happens when we need to find subtrees that are similar but not necessarily identical?
That's where things get really, really interesting.
Okay.
Exact matches. They're neat and tidy.
Right.
but similarity that opens up this whole new world of possibilities and challenges. It's like, recognizing a familiar face in a crowd.
Okay.
The features might not be exactly the same, but there's that resemblance that catches your eye.
So instead of looking for those like perfect replicas, we're trying to capture the sense of closeness or like resemblance between subtrees.
Right.
But how do we even begin to quantify, something as fuzzy as similarity when we're dealing with these like complex tree structures?
Yeah, that's a great question. One way to think about it is to consider, how much we'd need to change one tree to make it look like the other.
Okay.
So imagine you have these two small trees, like made out of building blocks.
Okay.
How many blocks would you need to move, add, or remove to transform one tree into the other one?
Okay. I'm visualizing this. So like if one tree has an extra branch, that's one change.
Right.
And if a node has a different value, that's another change.
Exactly.
It's like counting edits, but for trees instead of like text.
Precisely. And that's essentially the concept of edit distance.
Yeah.
In the world of strings, edit distance tells us the minimum number of operations,
Right.
like insertions, deletions, or substitutions,
Right.
needed to transform one string into another.
Yeah.
And we can extend this idea to trees as well.
So a lower edit distance between two trees means they're more similar structurally speaking.
Exactly. It's like saying, two trees are close relatives.
Right.
If their family trees only require a few tweaks to match up.
Right.
But calculating this for every single pair of subtrees can still be computationally expensive, especially when we're talking about these massive trees.
Yeah, that sounds like a lot.
It's like trying to find family resemblances in this giant genealogy database.
Right, so brute force isn't going to cut it here either.
Yeah, brute force is not our friend in this case.
So are there any like shortcuts or clever techniques to make this similarity search more manageable?
There are. One really cool approach is to use tree embeddings.
Tree embeddings.
Yeah.
Okay, this sounds a bit familiar. Didn't we talk about like representing subtrees as strings or numbers earlier? Is this like that but just fancier?
It is similar in spirit,
Okay.
but instead of using a single string or a single number,
Right.
we use a vector of numbers to represent each tree.
Okay.
The idea is to map those trees that are structurally similar to points that are close together in this high-dimensional space.
So instead of comparing branches and nodes, we're comparing coordinates in this like high-dimensional space.
Exactly.
Okay, that could definitely be faster.
Yeah.
But how do we even create these embeddings in the first place?
There are all sorts of different techniques.
Okay.
Some of them use random walks through the tree.
Okay.
Others leverage the power of neural networks.
Neural networks, now you're talking.
Yeah.
So we're basically letting the AI learn what features made trees similar instead of us trying to handcraft those features ourselves.
Exactly. That's the beauty of deep learning.
Okay.
Once we have these tree embeddings, we can use standard similarity measures like cosine similarity
Right.
or Euclidean distance to quickly compare them
Right.
and find those closest points in our embedding space,
Gotcha.
which will correspond to those similar trees.
So we've transformed this like complex tree comparison problem into a much simpler vector comparison problem.
Right.
Like we're replacing that messy tangle of branches with a nice, neat set of coordinates.
Exactly.
But can you give us a concrete example of how this like similarity detection would actually be useful in the real world?
Sure. Let's go back to that plagiarism detection example. Imagine a student, cleverly paraphrases a paragraph.
Okay.
They change the words, but they keep the core structure of the argument the same.
Right. They've just changed the decorations on the tree, but the underlying shape is still the same.
Yeah, exactly. Now, our previous techniques like string matching or even our hashing techniques, they might miss this.
They might not catch it.
Exactly.
Because it's not an exact duplicate.
Exactly. But by using tree similarity measures,
Right.
based on these embeddings, we can potentially detect that subtle plagiarism.
Wow.
We're not just looking for identical sentences anymore.
Right.
We're looking for those similar patterns of ideas.
That's really powerful.
It is.
Are there any other applications where this kind of structural similarity analysis comes in handy?
Oh, absolutely. Think about analyzing protein structures in bioinformatics.
Okay.
Two proteins, they might not be identical.
Right.
But if their shapes are similar, they might have similar functions.
Okay.
Or they might interact with the same molecules.
So tree similarity techniques could help us understand the relationships between different proteins and maybe even discover new drug targets.
Exactly.
That's incredible.
It really highlights how, these seemingly abstract computer science concepts can have these far-reaching implications in fields we might not even expect.
Well, we've covered so much ground in this deep dive.
We have.
From those basic concepts to those really sophisticated techniques, it's clear that the world of duplicate subtrees is vast and fascinating.
It really is.
And we've seen how these techniques can be applied to so many different things, from plagiarism detection and data compression to compiler optimization and bioinformatics.
It's amazing how many different areas these techniques touch.
It really is.
Yeah.
But even as we wrap up, I can't help but feel like we've only scratched the surface.
Yeah.
Are there even more advanced or specialized techniques out there for comparing these tree structures and finding those hidden patterns?
Oh, absolutely. There's a ton of ongoing research in this area. Researchers are constantly, pushing the boundaries. They're developing new algorithms, and they're leveraging the power of machine learning to tackle these increasingly complex tree comparison problems.
Oh, it sounds like there's a lot to look forward to. A huge thank you to our expert guest for guiding us through this fascinating landscape of algorithms and applications.
It's been my pleasure.
And to all our AI.Code.Cast listeners, keep exploring, keep coding, and keep those algorithms humming. We'll catch you in the next episode for another deep dive into the exciting world of computer science.